All right, there's a lot going on here trying to, as you try and integrate ODE events instead of fzero to stop your ODE 45 solution when the projectile hits the ground. So I thought I'd just record myself trying to go through things and troubleshoot. So we've got our vector velocities, our optimal launch angles that we're going to collect. So the idea is you pass velocity to Cannon solver, and we want to return the optimal launch angle. Okay, great. We got a whole lot of nesting going on, so we just need to be careful in terms of variables. And so one I'm just going to change. So I'm just going to go ahead and change our index variable here to j, since it doesn't matter, to make sure I don't cross anything later on. Okay, so this isn't used, right? So we just really need that optimal launch angle. So that's that. Looks like I've got, since it's nested, I have index variables that are going to be used elsewhere as well. So let me go ahead and change my index here to k, just to make sure I don't have any unintended consequences. Might be perfectly fine, but I'm extra careful like that, I suppose. Okay, so that's good. That was before. Alright, so here's where before we had fzero, and now we're going to try and use ODE events. Okay, so I'm going to delete this, okay, just to clear up space. Okay, so this is looking good. Okay, so we get rid of fzero. Okay, so what I'm going to do is, this is my event function. So you copied the template. So I'm going to copy it, comment it out here, and I'm going to put it near my actual rate function. Okay. And the reason I want to do that is my event function, right? So what's going to happen now is ODE 45, each time step is going to call my rate function to determine or to estimate the rate of change of my functions at that current time t. It's also now going to call upon my event function to see if an event's happened. So the input's going to look exactly the same. So I'm going to make it t and m as input, so it matches my rate function. What I'm interested in here is when y is equal to 0. Okay, so I'm going to cut that. Okay, so value. Okay, value is going to correspond to my event, or I'm looking for when this quantity is equal to 0. So in this case, value will be y. Is terminal. It can take on values of 0 or 1. 0 means when that event happens, mark it, but then keep going. 1 means terminal, quit. So in this case, it's going to be terminal. We want to stop when our y position is 0. And then direction could be -1, 0, or +1 in terms of if that quantity is decreasing, increasing, or I don't care when that event happens. So in this case, it should be on the descent. It should be -1. But if you weren't sure, you could just make it 0. So now with the event function up here, okay, I can define my options just as I did. Okay, and let me clear this out here just for space. Okay, so then when I solve my diffie-q, okay, I give it my initial conditions yet. Okay, I don't need the ith value, vx naught, vy naught. Okay, it should be, right, you're just passing a specific velocity here. And this is where I think this is nested up here. So we do need to be careful, because this uses little v, so it should be fine. Okay, but let me go ahead and make that big V. All right, so nesting can get confusing very quickly. So I'm going to make that big V my vector of velocities. just so that I'm not mixing it up with little v here, since this is nested. Since I'm explicitly passing it, it's going to look for that variable as an input. But just to be safe, I want to make sure they have different names. So now it's clear to me I'm just passing a specific velocity here. So v naught then is just going to be a single scalar. So vx naught and vy naught will be single scalars. So there's no pointing to the ith element. And you're right, I pass options. Okay. Alright, so we're going to have to gut a couple of these things. Okay, so at part 4 solver, what is this? I don't know, right? But what I should be calling is just like when I had fzero before. I'm going to call canon rate. Okay, when I used fzero, okay, the lower bound of my integral started at some value greater than 0. Okay, but now I want to start integrating at 0. So the way ODE Events is going to work is it'll integrate starting at time equals 0, and then it'll stop either when it gets to t is equal to my final time specified, or my terminal event happens. So I want this upper bound just to be some large number so that event happens first. Okay, that's great. I want to return the distance traveled. Okay, we just have the one event here, so I'm going to get rid of those just because it's not necessary. Let me pull out x to follow this notation, so I'll return the final x value. Okay, and then my error function isn't needed anymore. And now that I've done that, those variables don't need to be initialized. Okay, so assuming everything else worked. Oh, I see, this is part 4 solver. You definitely didn't want to call the top function. It says no input, so I just clicked run. Oh, I thought I'd clicked run. Okay, it says undefined function or variable v naught, line 7. Oh, it's got to be v. And what's my mass here? This looks like I get a straight line. Mass is 75 kilograms, so that's good. Theta naught. Okay, I'm going to make sure that since I'm nesting, there isn't some funny business going on with these variables here. So I think that might be happening. So up top here, let me call this theta naught opt. And let me try again. Okay, that looks better. Alright, because now I get that as velocity increases, my optimal launch angle increases and approaches a value close to 45. Okay, so let's see if we can't. Looks like we already have a lot of data points. What if I have 200 velocities? Does that help at all in terms of making this smooth? Cool. So it looks pretty good. Looks like if I really wanted to smooth it out, maybe I increase the number of angles considered. Let's see. Cool. So it makes it a little smoother. So there's optimal launch angle as a function of velocity. Okay, that's great. Yeah, and so that's case one. Since it should have worked before, okay, let's make it so that this also has an input of mass. And what I'm going to do up here, let's do M1 is 75 kilograms. And I can't remember what mass 2 was, but let me just type in 1 kilogram for mass 2, right? And you would have to update it. And then let me create a theta opt 1, all right, which will correspond to our plot with our optimal mass 1, optimal mass 2. Okay, so now here, besides velocity, let me give it as an input M1. Let's solve also with M2. All right, we can do both at the same time since we want the same masses. So let me plot optimal 1. Here's 2, the case with mass 2. And let's make this, okay, now that I've got more data points, just use lines. Let me label the two different cases. Or that's not label, that's legend. X label is V naught. That's in meters per second. Y label should be theta, and that's in degrees. Okay, I'm going to decrease theta back to 100 thetas, just so we see if this runs. Since now I'm doing it twice. And let's see if I get lucky. So as it's running there, res is underlined, that's just because it's not used. Right? Hey, looking good. Alright, so here's optimal launch angle is a function of velocity for mass 1. And then here's mass 2. So mass 2 actually looks like I go through an extremum. That's pretty cool. Since it didn't take that long, I can go ahead and I could use, say, 200 velocities. So look at your solution. I see now an error with my solution. And namely, with the lower velocity, it looks like optimal launch angle increases, goes through a max, and then decreases. Where I just assumed that it should continue to increase. And it mainly comes in here. And that my drag in the y direction is proportional to velocity squared. So it seems pretty cool, I guess, that launch angle increases, goes through a max, and then decreases with that small projectile. I wouldn't have guessed the extremum. I'm trying to think through my head. I mean, I just assumed that the drag was proportional to velocity. And I was thinking in terms of as velocity increases, drag increases. But, you know, I guess this is just an example that there's more to it than just that. So hopefully that helps out, and that you're able to use that to solve the problem. All right. Let me know if you have any other questions.